I'll begin with a word of prayer. Excuse me. Heavenly Father, we thank you for this day. Again, I thank you for these students in this class, and just ask you to be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Oh, I did have mission 4 here to turn back to you guys. I'll try not to name names. I think, oh, this other person's also here.
I've got mine. Oh, man.
All right, so I was covering the name. Sorry about that. I wasn't trying to make it too tricky. Here is the attendance sheet, in case I forget the top hat. And let's see here. I did have a verse for today. It kind of goes with last Friday, though. Come on, phone. Wake up. Here it is. This is Proverbs 18:2. A fool does not delight in understanding, but only in revealing his own mind. So, Proverbs 18:2. So anyway, that was about me, not you. Let's see here. So let me begin with a title here, which is Calculus of Matrices. Although, to be fussy, really what I want to talk to you guys about is if we have a matrix which is actually, I mean, to be fussy, we're talking about A as a mapping from the reals, let's say, to our m by n. All right. So technically speaking, this is a matrix valued function of time t. All right. For example, we might have a of t is t squared, t cubed, t to the fourth. That's simple enough, right? Or you might have b of t is equal to 1 e to the t cosine t hyperbolic sine of 3t. The matrices don't have to be, the matrices they don't have to be 2 by 2. It's just my example so far. We could also have something like this. X of t is, say, e to the t times 1, 2, 3, something like this. Could be the kind of thing I'm talking about. Oh, I meant to say, the laptop should be closed while class is going because there's probably not a reason to have them open. So, unless you're looking at my notes. Oh, top hat open. I'm not sure how I should take that. But anyway. Anyway, let's see. We go on. So these would be examples of matrix valued functions of time. I mean, technically the formula for them, right? The matrix is the assignment. The function is the assignment of t goes to a of t, right? T goes to b of t, t goes to x of t. Any questions about this? Do you guys get the big idea here? We can look at matrices which are full of functions, all right? And of course you could do things like evaluate, right? Like what would a of 0 be? 0, the 0 matrix. What would be a of 1 would be what? 1, 1, 1, 1, right? What would a of 2 be? 2, 4, 8, 16, and so forth. You could do things like that, right? But we can do more. We could take limits, but you guys don't like limits, and neither do I. So let's make a definition, which is this. dA dt, all right, is, let's just define it this way. dA dt, the ijth component, guess what it's going to be? It's going to be the derivative with respect to t of aij. So likewise, like the integral of, a dt, the ijth component of that is just literally going to be the integral of the ijth component dt. So we integrate and we differentiate matrices component-wise. All right? Now, of course, you could also do definite integrals, or you could do indefinite integrals, right? Like you could add bounds if you wanted. If you don't add bounds, you better add a different constant for every, for every entry, because you have no right to assume that the integration constant's the same in different entries. Example 2. So you guys tell me, what's the derivative and what's the integral of these things? So like what's dA dt? We got what? 1, 2t, 3t squared, 4t cubed. For this A, for this B, what we got? We got ourselves dB dt is 0, e to the t, negative sine t, 3 cos 3t. And what's dx dt here? Now here I'm just going to use a theorem that I haven't even stated yet, but if you've got a function times a constant vector, the way it works is you just differentiate the function and leave the constant vector alone. So dx dt is literally e to the t times 1, 2, 3 again. All right, let's integrate. The integral of a dt would be like, let's see here, 1/2 t squared plus, let's say, c11, 1/3 t cubed plus c12, and 1/4 t to the 4th plus c21. You don't have to use the notation that I'm using for the constants. It's just organized, 1/5 t to the 5th plus c22. All right, there you go. And we could go on like this, all right? Everybody on the same page with me? Do you feel like you can differentiate a matrix of functions? Like even if I didn't give this definition, I bet you could have done this, right? It's just the natural extension of what we already did if you've had Calculus 3 before. And if you haven't done Calculus 3, this is the part of Calculus 3 that nobody actually has trouble with. And so, now if I ask you guys to find the tangent line to one of these things, then all of a sudden everything would go up in smoke. But if I don't do that, we should be okay. I don't think I'm going to do that in here. I'll have to look at my homework again, though. Okay, so what are the rules of calculus of matrices, matrix-valued functions? So here's the rules theorem. What do you think the derivative of a plus b would be? What do you think the derivative of a times b would be? What do you think the derivative of a constant function times a matrix would be? What do you think the derivative of a constant times a matrix would be? So let me emphasize here, a and b are functions of time, f is a function of time. I'm assuming that they're all differentiable. To say that a matrix is differentiable means that all of its components are differentiable, right? So you guys will not be surprised when I write down dA dt plus dB dt, right? So you have that additivity. What do you think goes next? What we got? Any guesses? Yeah.
Would it be the product rule?
The product rule? How's that go here?
Not sure, since it doesn't commute.
Not sure since it doesn't commute is the most excellent answer possible. So the answer is dA dt times b plus a times dB dt. And therein lies the reason that in Calculus 1 I write the product rule as f prime g plus f g prime, because I'm preparing my students for this day. But you've been taught a different product rule, which is not simpatico with the anti-commutativity of matrices. So the non-commutativity of matrices rather. And so basically you just have to mind the order of A and B. Don't mess them up. Just do the product rule with the order of A and B stay the same. And here it doesn't really matter because f is a scalar function, so it's like df dt times a plus f times dA dt. You could put the f on either side because f is a scalar function here. So like whatever. And here, we just pull the constant out, which is really a special case of the one right above it. Right? In fact, notice that if you had that like dc dt was a matrix and it was constant, then if you had ddt of a constant matrix times another matrix, that would be the constant matrix times dB dt. Right? So you could pull a constant matrix multiplication out of the derivative. Yeah. That's cosh, hyperbolic cosine. You're not hallucinating. There is an h there. All right, so those are the rules. Let me prove one of these at least. I'll prove the interesting one, which is probably this one. So let's look at ddt of AB. How do we calculate the ijth component of that? What? That is ddt of aij. But how do we abij? So abij, remember by definition, was the sum over k of aik bkj, right? That was our definition of matrix multiplication at the level of indices, index calculation. But then we have an ordinary derivative. So we can pull the sum out of an ordinary derivative, right? And then what are we looking at? We're looking at the derivative of the product of aik and bkj. But what are those? That's just a product of functions of time. See, those are just ordinary functions of time. So going back to calculus 1, we know the product rule. Right? So we do the product rule here. So we got ourselves a dik dt bkj plus aik dbkj dt, which, by the way, is the sum over k of parentheses dA dt, the ikth component of that, times b, the kjth component of that, plus the sum over k of aik parentheses dB dt kj, where again I use properties of the sum to break it up. But what are we looking at? That's nothing more than, dA dt times b plus a times dB dt, the ijth component of that. But if these two things are equal for the ijth element, then they're equal. So that's how we prove. Every one of these rules is proved like this. All you have to do is use ordinary rule of calculus and sort through the definition of matrix differentiation as it's defined component-wise. It's pretty easy to understand why these things are true. And you can also understand why it was important that we maintain the letters ordered just as they happened, right? Because in order to recognize these as matrix multiplications, we had to have the same ordering of the letters as we did to start with. Otherwise, we wouldn't be able to identify them as matrix multiplications. Let's see here. Let's do an example. A little bit surprising, perhaps. What if we had like the derivative with respect to time of, I don't know, let's start with something like a squared. How's that go? What does it mean? So here I must be talking about a square matrix to make this make sense, all right? So I'm talking about a square matrix. How should this go? So what do we mean by a squared for a square matrix? Looks what? What does that mean? That's just notation for a times a, right? Which then gives us what? Product rule, right? So we have dA dt times a plus a times dA dt. And you can't just simplify that. It's not just twice a times dA dt, because we don't know that a and dA dt commute. In fact, you could try it out. For my example 1 and example 2, you know, quick calculation. Does this times that actually commute? You know, I don't, these don't generally commute. So we have to, it's like this is the best you can do. Let's see here. Example 4. Suppose B is constant. I'll let you guys work it out. What do you think ddt of a squared ba would be equal to? So you guys work that out, and I'm going to go get the coffee I brewed like 10 minutes ago. Do, 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 do. Do, doodly doo. I'm looking at my planner. I'm going to make sure I don't forget anything today. Yep. Oh. Oh. I still have things to do. I knew today couldn't just be as easy as showing you guys the calculus of matrices. Let's see here. Okay, so how did you guys do? I mean, what I would do here is I would do like ddt of a squared times ba plus a squared times ddt of ba. That's the product rule. Now I just worked out what ddt of a squared was in example 3. So that's going to give me like dA dt times a plus a dA dt times ba plus a squared b times dA dt, where I'm using the special property that if b is a constant, I can pull it out. Now, it might be possible to, I don't know if any of these like, you know, let me look at it, see if we've got any of the same things. Probably not though. Here I've got dA dt abba and plus dba and then plus a squared b dA. I guess there's nothing. I don't think anything here is alike, so you're just stuck with that. That's your answer. Yeah. Another thing I should show you guys, I wasn't planning this beforehand, but I think it would be good for me to show you guys this now. Example 5, something called the matrix exponential. What is the matrix exponential? So for a square matrix, A, the series e to the ta is equal to the identity plus t times a plus 1/2 t squared a squared plus 1 over 3 factorial t cubed a cubed plus dot 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 dot. In other words, the sum n equals 0 to infinity of t to the n over n factorial times a to the power n. This is the matrix exponential. Now you might say, why are we adding an infinite series of matrices, and who even does that, right? Well, the answer is everybody who does science and engineering does this pretty much. Like the matrix exponential is a big player in the story of multivariate analysis. It's a very important function of matrices. And the beautiful thing is, you guys remember Calculus 2? Remember all of, you guys loved convergence and divergence. Do you remember convergence and divergence? Right? And some series converged, some didn't, right? The thing is, this series converges for any matrix, period. Right? Just like the exponential, right? If you think about the ordinary exponential e to the ta, for what t does that converge for? The ordinary exponential e to the ta. What a does that converge for? What choices of a does that? I mean, if you pick any a, this converges for all t, right? And in the same way, this converges for all t. Now, what would the derivative of this be, do you think? Guess what? There is actually also a term-by-term calculus for series of matrices. And if you want to take the calculus of a series of matrices, you just differentiate term by term. So what's the derivative of I? 0. What's the derivative of TA? Just A, right? We're here A is a square matrix. I should really emphasize here that A is what? What kind of matrix? This is kind of important. Sorry, I kind of buried the lead here. Square constant. Sorry to use this hideous Carolina blue, but I guess it served its purpose. And then what happens when you differentiate t squared over 2? Well, you just get t, ta squared. And then we get 1 over 2 t squared a cubed. And if you did the next one, you get 1 over 3 factorial t cubed a to the 4th, and so forth and so on. So what happens if you factor an a out of that? What do you got? Factor an a out, we've got an I for the first one. We've got a TA from the second one. We've got a 1/2 t squared a squared for the third one. We've got a 1 over 3 factorial t cubed a cubed for the fourth one. Dot, dot, dot. What is that? Yeah, that's exactly the matrix exponential again, right? So the matrix exponential satisfies this beautiful identity. E to the TA is equal to A times e to the TA. That's pretty neat. We'll use that later. So I'm introducing it to you now because one of the things I've asked you in the computer project is to calculate this thing for some matrices. I'm fairly sure there's a built-in function in MATLAB to do that. I don't know what it is, but I have faith that MATLAB would do such a thing for such a central function of mathematical physics and engineering and math. All right. So, well, this kind of stuff is fun on its own right. It's not really why we're here. The real reason I'm covering this material is to address a certain gap in the differential equations class, which is systems of differential equations. You guys cover that a little bit depending on the semester, but I don't think it's covered fully. We'll cover it fully in here, because in here we have the technology to do such. So let's talk about a system of linear differential equations. So I just want to briefly give you an example or two to get you used to the idea, and then we'll talk about how to solve them. So example 6, maybe we're up against like dx dt is equal to, oh, let's say 2x minus y, or plus y, and dy dt is equal to, let's say, x plus 2y. So the differential equations we're going to look at, they'll always be eventually understood to be n differential equations and n unknowns, and they have to be linear in this sense. they're linear in the sense that I can translate this, right, into d dt of the column vector xy. Let me use x1 and y1 just to be more annoying. I mean x1 and x2 rather. So let me switch over to my x1, x2 because I do want to use the more efficient notation here in just a second. So let me switch to x1 and x2. That's more honest. So I've got a matrix times x1, x2. All right. What matrix do I want there?
2, 1, 1, 2.
2, 1, 1, 2. So that took you 0 mental effort in this course because that is this course. See, in Math 334, that would have actually maybe stopped us for a second, right? Because I would have had to teach you guys like a mini course in matrix math there if you hadn't had this course before. Of course, neither of these courses have prerequisites of one another, so it's annoying in that way, isn't it? But anyway, so there it is. In other words, a much more efficient way to look at this would be what we're looking at is dx dt is equal to ax. All right? Dx dt equals to ax. Now, example 7. What if I had something like dx1 dt, which is, by the way, x1 prime, is equal to x1 plus x2 plus x3, and x2 prime, let me be real boring, 2x1 plus 2x2 plus 2x3, x3 prime equals to 3x1 plus 3x2 plus 3x3. All right, great. This is equivalent to dx dt equals to ax, where x is equal to what? x1, x2, x3, and what's my matrix of coefficients here? We got it. Very good. So there you go. In a nutshell, that's how to set up. These are linear, homogeneous differential equations. So if the differential equation has this pattern, this kind of pattern, we can rewrite it as simply dx dt is equal to a constant matrix times x. All right. And so, like, basically, this is tantamount to saying that your system can be written in this way. dx dt is equal to ax, where A is a n by n constant matrix, all right? That's what we mean by a linear system of differential equations. Now, it turns out, if you had a higher order differential equation, you can always rewrite it as a system of linear equations through something called reduction of order. So, like, example 8, if I had, for instance, y prime prime plus y equals to 0, I could let x1 equals to y, and I could let x2 equals to y prime. So that would tell me that x2 prime prime is equal to y prime prime, but y prime prime is minus y. So lo and behold, we've got x1 prime equals to x2, and x2 prime equals to minus x1, which gives me dx dt equals to ax with a equals to 0, 1, minus 1, 0, I believe. And again, here x is like example 6. So a single, one second order differential equation, homogeneous linear second order differential equation, can be traded for 2 first order homogeneous differential equations. And this trick can be extended to higher order. So what this means is if we can solve